Hi, Michelle Glass here, and welcome to our third installment of our Chapter 20, Lecture 20, and our topic for this video is the cardiac cycle. The cardiac cycle is telling us really what's happening as the blood is flowing through the heart. So we're taking together the information we've already learned about blood flow, the direction of movement, the anatomy of the heart, and also then looking at that information about the pacemaker system and how the atria contract and then the ventricles contract, and putting it together in terms of how the blood is actually moving through the heart. For our cardiac cycle, we have two terms we want to make sure that we understand. We have the term systole and diastole. You've heard of these before, but maybe in the form of systolic blood pressure and diastolic blood pressure. Systole is talking about the contraction of the heart. So the systolic blood pressure is that initial push of blood through the heart and through the arterial system. And then diastole or diastolic blood pressure is talking about when that heart is relaxed and there's no more push. So that high number would be the systolic, and then the low number would be the diastolic on your blood pressure. Now, I've highlighted the S and the Y for systole because the SY here is the same prefix as what you have in synthesis. The SY is talking about coming together. So that might help you to remember that contraction is talking about this coming together of the muscle cells. Okay, so let's take a look. So you start your cardiac cycle looking at when those atria contract. So you're looking at that event there. So we've already had the depolarization of our SA node. It's already traveled the internodal pathway to the AV node, leading to contraction of the atria. What you should see here is that when those atria contract, that's that final push of blood into the ventricles. So when we're looking at the atria contraction, that final push is about 30% of the total volume. So that final push, there was blood already down there in the ventricles to start with. Then what we see happening is the ventricles begin to contract. And when this happens, that pressure starts to build, and that initial push of pressure, and as the blood starts to be pushed up back toward the atria, that's going to cause the closure of those right and left AV valves, or the tricuspid and the bicuspid valves. Now notice that this stage right here in the cardiac cycle is referred to as isovolumetric contraction, where that prefix iso means same and volumetric is talking about same volume. So in this case, every valve is closed. There is contraction of the ventricle, there is pressure building in the ventricle, but the blood is not going anywhere. It's not regurgitating or going back out into the atria, but it's also not leaving the ventricle, going through the pulmonary trunk or going through the aorta. The amount of blood that you have in the ventricle at this point is going to be referred to as the end diastolic volume, or the EDV. So that's talking about all the blood that has flowed from the atria to the ventricles during the passive filling time. That's like 70% of the volume. And then that final push of blood, that remaining 30% that gets pushed down into the ventricle. All those valves close up, and then that isovolume, that amount of blood that's there during the isovolumetric contraction is our end diastolic volume, because the ventricles are no longer relaxed. They are now contracting. And this is the amount of blood that we have to start with. So I'm going to use my sponge to represent what's going on here. All right, so I have a nice dry sponge. And I'm going to say that I've had passive flowing of blood from my atria to my ventricles. I kind of want to make this look like a 70-30. Oh, I didn't quite make it. Okay, so let's pretend I did a good job. So my sponge has soaked up some water passively, right? And then I'm going to let it go ahead and get all the way soaked up. So that's my final push from when my atria contract. So however much fluid I have in my sponge at this time, let's call that my EDV. my end diastolic volume. Okay. Let's go back to looking at our heart. The ventricles are continuing to contract, and as this happens, more and more pressure is building in the ventricle until you have so much pressure that you just push open those semilunar valves, the pulmonary semilunar and the aortic semilunar valve, and the blood starts flowing through that pulmonary trunk to the lungs or out through the aorta to the body. This is called ventricular ejection, right? Ventricular ejection. Let me grab something else for my demo here. Okay, so what I wanted to grab was a cup. Let's pretend it's our body. And I'm trying not to soak my laptop. Scary. Okay. So I've got all my fluid in my ventricle, my EDV, and now I'm going to do my squeeze and hold. That's my ventricular ejection. I squeezed and held. And so this amount of blood that leaves my heart, leaves my ventricle, is going to be called my stroke volume. So during one cardiac cycle, how much blood are you able to eject? Meaning that's what's going to go out to the body. Really, we're going to care about stroke volume in the systemic circuit more than in the pulmonary circuit. So when you talk about stroke volume, you're doing that measurement of how much blood is going through the systemic circuit. Okay. What we see happening next is that we move into that ventricular diastole. Remember, that means relaxation. So the ventricle relaxes, meaning there's no more push of that blood up, out through the semilunar valve. And instead, you have some gravity causing that blood to move back down in both the pulmonary trunk and the aorta. And when the blood moves down, based on the anatomy of the semilunar valves, it shuts them. So you have some blood that comes back down, shutting those semilunar valves. Even though the ventricle is still contracting, or excuse me, even though the ventricle is relaxed, it's not contracting, there is still pressure inside the ventricle. And so those right and left AV valves or tricuspid and bicuspid valves are still shut at this point. So now we don't have any blood flowing into the ventricles or out of the ventricles, and our ventricles are relaxed. And so this is called isovolumetric relaxation. All of the valves are closed. Now take a look at my sponge. I've squeezed it. I've got all of the fluid out that I can get out, but it's still wet. I'm not sure how well you can see that, but it's flexible. You guys have worked with sponges before. You know, a super dry one is not this bendy, right? We'll do this in class too, just so we have that extra feel. The fluid that's left over is going to be called the end systolic volume, ESV. So I've done my contraction, I've done my squeeze and hold. I can't squeeze out anymore, but my sponge is still damp and there's still blood inside my ventricle. So depending on how effective your squeeze and hold is, you're going to have more or less blood left over in the ventricle, but it's not going to be completely empty. The amount of blood that's left over is the ESV, okay? So going back to looking at our stroke volume calculation, is the EDV minus the ESV. So how can we measure how much blood actually left the heart? We can take a picture of the blood during isovolumetric contraction, and we can see, or the picture of the heart, we can see how much blood is actually inside the ventricle. Then we can take a look at the heart and the isovolumetric relaxation, and we can see how much blood is left over. When you take your starting amount, your EDV, and you subtract your ending amount, your ESV, that tells you how much blood actually was ejected from the heart. That's your stroke volume, okay? We'll be talking about those terms again, so you need to be comfortable with that. Okay, this is where we were in our cardiac cycle. So we're in the isovolumetric relaxation. The ventricles are in diastole, so that means they're relaxed. All of the valves are closed. There's a little bit of blood remaining. And then what we see happening is the pressure goes down enough in the ventricles to cause those AV valves to open. Right and left AV valves, tricuspid, bicuspid valves open back up. So now we have this period called the passive filling time, where we have blood flowing from the body or from the lungs into the atria and straight down into the ventricles. Most of the blood that makes its way into the ventricle is occurring here during a passive filling time. So like 70% of that total EDV is coming during this passive filling time. So this would be why you would want to have a slower heart rate, so you have more time for the passive fill before you do that remaining 30% forced into the ventricle and then the ventricular contraction. The more time you have for the passive filling, the more total blood you're going to get in that ventricle to pump through the body. Okay, so a slower heart rate is desirable to increase that filling time. Okay, so now let's kind of try to go through the animation. So we'll go through it a couple times. So we have our forced contraction of our atria, pushing 30% of the blood, remaining 30% into the ventricles. The ventricles begin to contract, forcing closed the AV valves. This is our isovolumetric contraction. This is our total amount of blood we're ever going to get in the ventricle, so our EDV. The contractions continue, forcing open semilunar valves, and we have the ejection, and then we have our ventricles starting to relax, which is going to cause that blood to flow back down the pulmonary trunk and the aorta, closing off those semilunar valves. This is our isovolumetric relaxation, and the remaining blood that's in there is the ESV. Then we see that our pressure drops so that those AV valves open and we get that 70% filling time. So let's go through it kind of quick so maybe it looks more like an animation. And let's actually see if we can go back to the beginning. Go through it twice. Okay, that's our cardiac cycle. Stay tuned for more.